Well, hello and welcome you to Mr. Robinson back here with yet another brand new exciting video, all math-based of course. And as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step on aside as we conclude Chapter 8 in the Big Ideas Math Integrated Math 2 textbook on something called the triangle proportionality theorem, or in general, proportionality theorems. There are multiple of them within the same breadth. This is the last section, so following this would be review and the test and cumulative assessment and things like that. This was all leading up from dilations to similar figures to proving triangles similar and all that. And now we go to this one. This one's also known as the side splitter theorem. That's what I more famously call it. So if I accidentally ever call it that, apologies. But let's jump straight into what this lecture thing's going to look like. If you want to check down below in the description section, you'll find this PDF for this thing as well. We'll see what this thing has. There is a nice problem set for which we are going to do some problems hereafter and find the timestamp once again down below to follow along with exactly what we're doing. Okay, let's go ahead and look at how we're going to use proportionality theorems and partition directed line segments. I honestly don't know what that means yet, so we'll figure out what that actually means together. Okay, the triangle proportionality theorem states this. If a line parallel to one side of a triangle intersects the other two sides, then it divides the two sides proportionally. Now, first of all, they don't say necessarily just mid-segments. However, this would also apply for mid-segments. But what they're saying is, if these two lines are parallel, then RT over TQ equals RU over US. It's not just this over this that we've been doing before. This is why, like I said, it's also known as the side splitter theorem. The side splitter theorem is not just for triangles. I think that's the difference. But this is why it's also known as the side splitter theorem. This side is literally split into these two parts, and this over that equals this over that. Pretty nifty stuff. It's a proof that we're going to have to do later, it looks like. And the converse of the triangle proportionality theorem states that if a line divides two sides of a triangle proportionally, then it becomes parallel. You know it's parallel. So if this over this equals this over that, then that means these are parallel to each other. So the converse holds up. And those are, I suppose, the two proportionality theorems. I don't know what the directed line segments, though, are. I got to think of what that means by name. I'm not sure. We'll see when we hit those. So first example, finding the length of a segment. In the diagram, they're told that these two things are parallel, so you are going to be able to set this thing up. This is people's favorite theorem as far as just going like, I just get to point to this and this and this and that. But we're going to set that up. RQ, the missing side length, which is what they want to find, over QU, 9, equals RS over ST, 4 over 6. And I would generally reduce before I cross multiply or whatever, but multiply both sides by 9. 2/3 of 9 is 6. That is the length of RQ. It would be 6, like that. And a lot of things will be like that. We'll probably have some that are algebraic as well. Let me look at these. I'm skipping the example here. I'm going to look at what this thing says here. The theorems above also imply the following. The contrapositive of the proportionality theorem. Now, if you don't know what a contrapositive means, it means take the original theorem and say, if not this, then not that. So they're going to say, if these two are not proportional, then these two are not parallel. So let's see if they say that. If these two are not proportional, then they're not parallel. The inverse is where you take the knots of the original. And this also implies this as well. If the lines are not parallel, then those things are not proportional. Mostly because the contrapositive of the converse is also not true. See, not every theorem's converse is true. Whenever they state them, then cool. But all of these are also the case, that if not, then not. I wonder if they're going to run into that for us as well. Solving a real-life problem. On the shoe rack shown, BA is 33 centimeters, right here, 33. I shouldn't have to use my mouse. Hold on. Actually, I wonder if they label it. I don't see it. But BA is 33, CB is 27, CD is 44, and DE is 25. I guess this is one of those cases. Explain why the shelf is not parallel to the floor. Because these aren't in proportion to each other. 27 over 33 doesn't equal the same as 44 over 25, which is kind of what they're showing there. 44 over 25 is that number. 27 over 33 reduces to 9 over 11. They're not the same thing. Because they're not in proportion, then they're not parallel. So I guess they're going straight from the implication to that. Okay, the three parallel lines theorem. If three parallel lines intersect two transversals, so lines parallel, two transversals, then they divide transversals proportionally. I guess, I would call this side splitter theorem, but basically UW over WY equals VX over XZ. So a triangle could basically be split up by multiple parallel lines as well. It's something they may eventually do. But it's the same kind of thing in that side splitter theorem kind of way. So using the theorem, let's take a look at this example. In the diagram, angles 1, 2, and 3 are all congruent. And we got all these measurements, 120 yards, 150 yards, 300 yards. I imagine they're going to ask us to find the length of GH. Yeah, HG. So corresponding angles are congruent, therefore these are parallel. That's the converse of the corresponding angles theorem. So parallel lines, boom. If we have parallel lines, then we can use the proportionality. CD over DE equals HG over GF. And they have a version of that. They set those equal, in that, or they substitute there, cross multiply, whatever they solve, they get 240. Oh, they need to find the length, the distance HF between Main Street and South Main Street. So they're going to add the 240 you get with the 120. Now, this is a case where this is not a triangle, so you're less likely to look at this in the way of doing this over this equals this over this anyway, because it's not triangles that are similar. You can form similar triangles out of it and, do stuff when these meet here. But this is where that side splitter theorem takes more form, and you find that 240 separately, add it to the 120, and then you go from there. Okay, let's keep moving forward. Let's look at the triangle angle bisector theorem. I forgot this one. I forgot this was a part of it. If a ray so I guess it's not just the side splitter theorem. If a ray bisects an angle of a triangle, so here, bisecting boom, boom, then it divides the opposite side into segments whose lengths are proportional to the lengths of the two other sides. You can divide AD by DB. That's the same thing as CA over CB, like that. And there's more than one way you can write it, right? I could also do this over this equals this over this. There are a lot of different ways to go about it. There's, of course, a proof within that it looks like we're going to have to do. Yeah. So we'll go to it when we are ready. It's all about triangle similarity, folks. It's all about that. Okay. Because proportions don't set up like that unless you have that kind of proportionality. Using the triangle angle bisector theorem, we have this situation right here where you have an angle bisector. And they say these two angles are congruent, QPR and RPS, therefore angle bisector. So because it's an angle bisector, you can apply that theorem. So they're going to place an X right here where you're trying to find that length. It's just easier to write than RS, I suppose, is what they want to do. Oh, even more so, they're going to use it in the subtraction. The entire length is 15, so if this is X, then this guy here is 15 minus X, which they're going to work out. This over this equals this over that. 15 over X minus X over X equals 7 over 13. And then the cross multiply and solve. You're going to get an X value of 9.75, which is RS is length. Let me move myself over. I feel like I'm in the way. I feel like I'm still in the way. Some more examples for you to check, and check. All right. Partitioning a directed line segment. What's this about? A directed line segment AB is a segment that represents moving from point A to point B. The following example shows how to use slope to find a point on a directed line segment that partitions the segment in a given ratio. Honestly, I don't know if I've seen this before. I don't think I know what this is. I know what the word partition means, but I don't know what they're doing here. Find the coordinates of point P along the directed line segment AB so the ratio of AP to PB is 3 to 2. Ah, gotcha. So they're coming up with some point that's going to be on, it's down here. They're going to be coming up with some point that's on here so that, again, you have that 3 to 2 ratio. You want to try and find, I guess, 3/5 of the way. I'm trying to think, yeah, 3/5. 3/5 of the way over. Because 3 to 2 means that if this was 3, which is not really, if this was 3 and this was 2, then you're at the right point here, P. So technically, this is 3 to 5 all the way over here. So let's read what they say and go after that. In order to divide the segment in the ratio 3 to 2, think of dividing or partitioning the segment into 3 plus 2 or 5 congruent pieces. So take this entire length, divide it into 1, 2, 3, 4, 5 pieces, and point P is the point that is 3/5 of the way from A to B. So that partition will lead us to there once we're 1, 2, 3/5 of the way there. Makes a lot of sense. So you use that slope of AB as rise over run. For once they're actually... I guess that makes sense because this is a point on the graph. I was going to say for once they're actually using the slope to work out distance instead of using distance formula to find that, but this actually makes sense because you need to find a point that's on the line. So instead of going up 6 over 3, let's go 3/5 of 6 and 3/5 of 3 to get there, which is up 3.6 and over 1.8. Okay, that makes sense. Listen, I haven't done this before. I haven't seen that phrasing before, but this totally makes sense in what you're doing. So the coordinates, 3/5 of 6 is 3.6. You add that to the 2. That's already A's Y value, and you get 5.6. Boom. And then you add 1.8 with the 3 to get your X value of 4.8 right there. So P is at that value. Totally works. I got it. And I'll explain it more for other problems as we build into it. There's some compass construction. Ooh, I wonder if that means we're going to actually do that, but that gives us directed line segments here. Let's see how they do this. Place the point of a compass A and make an arc of any radius. Label the point using D. Using 3 can make 3 more arcs. But how do you know that that's 5 away? I don't know if I'm good with what they're saying here. Draw AB of any length. Choose any point seen on an AB. Place the point of a compass at A and make an arc of any radius intersecting. Of any radius, I see. Label the point intersecting D. Wait, what are we doing? Construct the point at L1 so the ratio is 3:1. Sorry about this. I'm just looking at what this is. AL to LB. Oh, right here is 3:1. So they don't really care about C. C is not relevant for this thing. That's just the name of the ray. Okay. Well, if we have to do a problem like that, we'll do it together. I was just looking into that. Okay, so that's the end of the lecture. Sorry about, I really do wing those lectures, guys. I never look at it to begin with clearly. Let's go and do the vocabulary and core concept check. Complete the statement. Number 1, if a line divides 2 sides of a triangle proportionally, then it is parallel to the third side. So if you have that proportionality, then it's parallel. This theorem is known as the then it's parallel. This is the converse of the triangle proportionality theorem. Excuse me. I'm sure the sound effects are just ASMR to your ears. Again, I stuff food before I record these to make sure that I don't go hungry recording them, because these can take hours sometimes. Triangle proportionality theorem. They sure did not account for that small blank when I wrote that. In triangle ABC, point R lies on BC and AR bisects angle CAB. Write the proportionality statement for the triangle that is based on the triangle angle bisector theorem. It will really help to make a triangle out of this and see where these things go. So let's say I made this triangle right here, and this isn't going to look beautiful by any stretch, but I draw an angle bisector, like that. Let's see what we're calling everything here. So point R lies in triangle ABC. Point R lies in segment base BC and AR. So here's gonna be A, B, C, and here's R, and here's the angle bisector portion. So he said write the proportionality statement for the triangle. Now there's more than one way you can write this. They've been doing a lot of taking the bottom parts, this over this to begin with. So I can say BR, the length of segment BR over the length of segment CR equals, and then you go back to this triangle, the length of segment AB over the length of segment AC. You know what I just noticed, and this will apply none to you, that probably, maybe it takes hold in the trig unit, actually. Never mind. I'm going to leave it. I'm just going to say it has to do with right triangle, similarity in right triangles. They probably save it for the trig unit, which is the next chapter. I was going to say, you know what I noticed is we never did that one. All right, so that is the answer I'm writing to this one, and it helps to make the drawing to see it. Again, there's more than one way you can write it. I could do AB over BR equals AC over CR. Totally fine. But those are not different triangles that way. All right, guys, so we are going to jump into the whole problem set, and we hit from problems 3 to 40 something. I'm not sure. Let's see what it is. Problems 3, whoopsie. Let's go problems 3 to 40, literally. 3 to 40. Okay, in exercises 3 and 4, we're going to find the length of segment AB. Now, if you're just jumping in for the first time, pity, you should have seen the lecture. There's something called the triangle proportionality theorem that states we can do, and I'll write out what the things are beforehand, at least to begin with. Well, these two, it's just 2 questions. Find the length of the segment AB. We can divide BC. I'll put CB. We can divide. I'll do AB. AB by BC, and that's the same thing as ED over DC. This is where these sides are kind of split in that way. So this is this over this equals this over that. Now AB is our one unknown, so I'm going to say AB over and BC is 3 equals ED is 12 over DC is 4. Now 12 divided by 4 is 3. Multiply both sides by 3, you get AB equals 9. So 9 is 3 times the amount of 3, just like 12 is 3 times the amount of 4. And this does apply in triangles in this way. You don't need to do the big part of the triangle fully for that. Okay, number 4. Let's find the length of AB again. And let's just set it up the way that we see it from top to bottom. AE over ED equals this unknown AB length over BC. So that's 14 over 12 equals AB's unknown length over 18. 14 over 12 is 7/6, and I want to use that because we're about to do, I can multiply both sides by 18 here. So 7/6 of 18. 18 divided by 6 is 3, times 7 is 21. So that is the length of AB, 21. All right, numbers 5 through 8. We're going to determine whether the lines are parallel. Now, the lines are only parallel, and there's some that probably will be and won't be. The lines are only parallel if you have that same proportionality. This is the converse of the triangle proportionality theorem. So we want to test something like, for example, does LK over KJ equal, in question, LM over MN? So if this over this equals this over this, then that's true. And by the way, I don't know how much I made mention of that for the first two sets here. The lines are parallel, which allows me to do that proportionality. You can't do it just because. You'd have to know that the lines are parallel for that to happen. I don't know if I mentioned that. Okay, so here we're trying to see if the lines are parallel. Are these things in proportion? Let's check and see if 8 over 5 is the same thing as 12 over 7.5. 8/5 can't reduce. I'm going to leave that like that. And sometimes you can use a calculator for these kinds of things. If I double these here, I get 24. Let me just write this on the side. I get 24 over 15, and I can divide those by 3 to then get 8/5. So does it equal? Yes. You get 8/5 equals 8/5 essentially. So that is a good old check. That is true because before it was in question. So yes, KM is parallel to JN because the proportionality holds. Number 6. Let's just go again from top to bottom. This time I'm not going to write out the letters. I'll go straight to it. 22.5 over 25. Is this the same as 18 over 20? I believe that is, knowing what how these numbers work here. 22.5 doubled is 45. I'll get 45 over 50. I can reduce this one by dividing by 2, taking half, and that's 9/10. And 45/50 is 9/10 as well if you divide those by 5. So yes, that one also pans out as it was in question. Let's see if I can do that each time. So yes. If the proportionality holds, then those lines are parallel. Number 7. Imagine we got to get some no's here in a moment. So number 7, let's try 24 over 15. Is this the same as 18 over 10? At least it's easy fraction reduction, so let's try that. Divide these by 3. You just saw this before. This is 8/5. 8/5. And 18/10, you can divide those by 2, and you get 9/5. 8/5 don't not equal no. 9/5. This is a no. These lines are not parallel in this situation. We gave it a shot. And I didn't look at the drawing, but if you look at the drawing, it doesn't look parallel. I think that these books are really intent on drawing things as to scale as possible. So they're like, I'm not going to make it look parallel if it's not parallel. Are you nuts? So maybe they tried that here. And I can't tell on this one, but when I look at the numbers, I'm going to say probably not. Does 35 over 16 equal the same thing as 34 over 15? Heck no. if you're, think batting average, or sorry, I want to see this the other way. Think 16 out of 35 and 15 out of 34. Someone goes into an at-bat 15 for 34. Good average, by the way. And they get another base hit. They're 16 for 35. Do they have the same batting average as before? No. Can any of these fractions reduce, by the way? No. This is a big whop whop. Straight off the bat. Heck no, those lines aren't parallel. Probably as close as you can get and make that guess. And the decimal approximation is pretty close, but not quite there. Much closer than 8/5 and 9/5 at least, which is 1.6 and 1.8. Okay, in 9 and 10, use the diagram to complete the proportion. So this is I forget the name of the thing. I like to call it side splitter theorem, but 3 parallel lines cut by 2 different transversals. You have proportionality within, like this over this equals this over that kind of thing. And so we can build that up. Oh, actually, hold on. They wrote some stuff. That's the whole thing we're doing. So BD over BF. So let's see where that goes. BD... Where's BF? Oh, they did this divided by the whole. So check that out. This divided by the whole equals, and we must probably have to find this guy that corresponds, CE, because CG is on bottom. It's the whole bottom whole, therefore. So CE. CE is the thing on top that we're trying to find over CG. Maybe it's not as side splitter as you want it to be, but it still is a proportionality that applies to these things. Because listen, these aren't triangles. And yes, they're built within triangles in a way, because I could continue these lines until they do intersect and make a triangle, but these parts still do that thing, which is essentially where these proofs would go. All right, number 10, CG over something equals BF over DF. Let's look at what those look like. BF, let's start with writing what BF over DF looks like. It looks like it's just kind of the opposite. Oh, here we go. BF over DF is on that side. Here's CG on this side. What corresponds with DF on the bottom? EG. EG right here. So that would be an EG value right now. Yeah, totally. All right, let's move forward. Numbers 11 and 12, find the length of the indicated line segment. Basically, still based off some of that side splitter theorem stuff. So they want to find the length of segment VX. VX is right here. Now, because of the right angles that you see, which would kind of be of congruence, you have congruent corresponding angles. The converse would state these lines are parallel. Because these lines are parallel, you can then use that proportionality. I want to find the length of Vx. And I can say that YW, I'll write these letters the first time, YW over WU, look at that left side. Now look at the right side, equals ZX over XV. They wrote VX, so I'll write VX. YW over the equals. Okay, so YW is 20. WU is 8. ZX is 15. VX is left for us to find out. I could cross multiply, but I could also reduce. If I divide these ones by 4 here, I get 5 halves. Now let's go to cross multiplication, if you will. That's 5 times Vx equals 30. And divide both sides by 5, you get Vx equals 6. 6 units for Vx. Number 12, let's find the length of segment SU. Once again, we have sets. Now this is pretty interesting how they designed this. They have congruent corresponding angles here, which make these lines parallel. And congruent corresponding angles here, which makes these lines parallel right here. Boom, boom. So 2 lines parallel to the same line are parallel to each other. So all 3 are parallel. What are they trying to find? The length of SU. So SU is here where we have 8 and 12 and 10 and this unknown SU. Let's write SU first. SU over dat dare 10 is the same as 12 over dat dare 8. Hopefully you see how I'm going about that. I did this over this equals this over this. Again, the proportionality here, it's less because you don't see it in triangles, but when you see what's supposed to correspond, I think you're going to start to get a pretty easy buildup of how you work it out. So SU is 10 times 12 eighths is 3 halves. 10 divided by 2 is 5 times 3 is 15. That is the length of segment SU. All right, let's go to numbers 13 to 16 where we find the value of the variable. This is the, I forget the name of the thing, triangle, angle, bisector, proportionality, theorem, something or another. And, you know, we're going to prove this stuff later, so I don't need to bother my time in describing it now, so we'll just do that. But versions of this thing is when you do have the angle, bisector, in a triangle, it's like this over this equals this over this kind of thing. Or any way you want to put it. 8 over 4 equals y over 6. Not any way you want to put it, but any way where parts can correspond in any sort of way. Let's start from the way that they've kind of written them before, like 4 over 6 equals 8 over y. It was the first way that I drew it out. The bottom parts that's bisected and all that. 4 6 is 2/3. You know what? Let's not reduce this one. Let's just cross multiply. 4y equals 48. And divide by 4, you get y equals 12. That's its length. All right, there's one way to write the proportion. Now let's try another way. So I did the parts along the bisector first. Now let's do it a different way. Let's try something like 3 over z equals 4.5 over 1.5. 3 over z equals 4.5 over 1.5. Now, there are so many ways I'm going to do it correctly. It's hard for me to say what you don't do. I don't do 3 over 1.5 is 4.5 over z. Those parts don't correspond in the two different triangles. It just doesn't make sense. Keep it 3 over z one more time. 4.5 over 1.5, guys, that's 3. 3 over 1. You know what z is? Just by looking at that, z is 1. Z should be 3 times smaller than 3, just like 1.5 is 3 times smaller than 4.5. That's just how it's going to look. That's how it's going to work. 3 over what is 3 over 1 is what I went off of. All right, number 15. Now, 15 has one little tricky bit in showing this entire 29. However, 29 is composed of 11 and the number 18. Now, you don't really want to use the 29 in and of itself. You'd like to use the parts that are kind of split up from this. So I can do, for number 15 here, let's do something like 16.5 over p. That's those top parts of the left triangle and the right triangle. Now let's do the bottom parts of the left triangle and the right triangle. We will use that 18. 16.5 over p equals 11 over 18. And I regret not doing 16.5 over 11 because that would have reduced it to 3 halves. But let's just make with it what we can. I regret not doing that now. I kind of want to now. Oh well, cross multiply. I don't know what 16.5 times 18 is. Let me do that. 16.5 times 18. So although you can do it any sort of way, sometimes there are better ways. 297. So 297 equals 11p. And, 297 divided by 11. Everybody knows that. 25. Everybody knows that one. Come on. Wait. 27? Shh. All right, 27. Okay, number 16. See, 16 has the same conundrum, if you will, where 16, the length, is the whole thing, but I don't want the whole thing. I want the split part. How did I get 18 here? I did 29 minus 11. So I have q here. How am I going to get this length with this being 16? It's 16 minus q. So that guy's 16 minus q. So let's go for the, let's just go for those bottom parts before we mess something up. Let's do q over 16 minus q. So that's the top triangle and the bottom part of the triangle, if you will. Equals, now that's 36 over 28 on this side. And I think this will help me reduce this fraction and do more things. If I divide these by 4, I will get 9 over 7. Let's cross multiply, and I get 7. By the way, that's a 9. That's a q. So 7q equals 9 times 16 minus q. Making us work. 144 minus 9q. Add 9q to both sides, you get 16q. Divide 16 by both sides, you get q equals 9. That should be the length there. Okay. All right, so that's number 16. This is going pretty fast for those parts, and maybe this is the slowdown. I'm not sure. I see construction. I did not know if we were going to get it, but we do. And these are those graphs. So let me do some copy-paste stuff now on graphs. And I'll make sure to attach graph paper on YouTube. In exercises 17 to 20, find the coordinates of P along the directed line segment AB so that AP to PB is the given ratio. Okay, so I kind of saw this in the lecture bit. I understood what it said, but I didn't explain it enough to the group when I said, okay, here's what you do. I think it makes more sense to see it in progression. So A is here, B is here. What's really nice is if you've done things with me before when it comes to distances, I'm more of a Pythagorean theorem guy, I'm more of a counting slopes guy, I'm less about distance formula, midpoint formula, that kind of stuff. And this will kind of play to that a little bit. So here's A and here's B. We need to do a 1:4 ratio from A to B with a point P that is somewhere from there to there. So here's what's going to happen. The 1:4 ratio means that P is going to be at some point. It's probably going to be somewhere around here, but P is going to be at some point so that whatever length this length is 4 times as much. This could literally be the lengths 1 and 4 or 2 and 8 or anything like that. But the point is, this is not 1/4 of the way there, but 1/5 of the way there. We're splitting up, 1 plus 4 is 5. And we're going to split this up into 1, 2, 3, 4, 5 The distances are 1, 2, 3, 4, 5 parts, and we're just going to go 1/5 of that way. Okay, so we got to travel 1/5 of that. So here's what we do. Let's determine what this slope is, if you will. How far down do we have to go? How far left do we have to go? And then we'll end up going 1/5 of that. So this is down 2 and left 1, 2, 3, 4, 5 over here. So let's take 1/5 of -2, which is -2/5, or -0.4. That's how far we're going to go down instead from A. A being at 8, 0 means we're going to go down 1/5 of that way. So P's points are at some x, comma, we haven't found that yet, and y is 0 minus 0.4. The x value, we're going to take 1/5 of -5. I just don't know how to show the work well, which is -1, which means we're going to go 1 to the left of 8. So 8 minus 1. So P's ordered pair will be at 7, comma, -0.4. Let's do those ones in black here. So black, like that. So P will be at 7, comma, -0.4 right here. There is P. And there's the work shown for it. All right, let's do it again. 3 more times. Number 18. A is at -2, -4. B is at 6, 1. I wish they were further apart in general. This is probably fine. B is at 6, 1. This ratio is 3 to 2, which means we want to go 3/5, because 3 plus 2 is 5. We want to go 3/5 of the way from A to B to go to P. So let's find out that rise over run. We'll go 3/5 of the rise, 3/5 of the run from A, land on that point. Up 1, 2, 3, 4, 5, and over 1, 2, 3, 4, 5, 6, 7, 8. Never fans of going integer amounts, are they? So 3/5 of 5 is 3. 3/5 of 8 is 4.8, because that's 24/5, so 4.8. So we're going to go 3 up, from A, 1, 2, 3 at -1, but an easier way to do that is just to kind of locate P here. P, we're going to go from -4 to 3 up from there, and we're going to go from -2 to 4.8 over from there. So P will be at 2.8, comma, -1. That's at 1, 2.8-ish, comma, -1. Just find the -1, and I think you'll just say, okay, there's the 2.8 from there. At least that makes sense for it. And that's 3/5 of the way. It's like 1, 2, 3, 4, 5. You know what I mean? Like that. Now, the 3 to 2 ratio means whatever this length is, this is that amount in comparison. Let's go to number 19. Okay, A is at 1 comma 6. See, suddenly it did slow down. B is at -2, -3. And our ratio is 5 to 1 from A to B. From A to B. So 5 to 1 ratio from A to B. 5 plus 1 is 6. Easiest math you get to do. We will go 5/6 of the way from A to B. Let's find out A's rise and run or fall and run here. How far down, how far left. Take 5/6 of those numbers. From from 6 to -3, that's a fall of 9. From 1 to -2, that's a run to the left of 3. We're going to take 5/6 of -9, which is -15 halves, which is -7.5. Right? Because 9. Sounds right. Yes, that is right. And then 5/6 of -3 is -2.5. Okay, so we're going to go 7.5 down from A and 2.5 to the left of A. So P will be, instead at 1/6, I'll write it like that. Instead of at 1/6, we'll go 1 minus the 2.5 and 6 minus the 7.5. So P will be at -1.5, comma, -1.5. So there should be a point right there, right there. That is P. That is 1, 2, 3, 4, 5. That is 1, 2, 3, 4, 5, 6 of the way to B. And looking good, looking good. -1.5, comma, -1.5. And I like that they have decimals here. They allow us to kind of free will that. We'll see if they ever test that even more. All right, number 20. A, oh, this is interesting. Let me first copy paste this. A and B are at these places, but look at the ratio, say 2 to 6. I mean, what is 2 to 6 if not just 1 to 3? I wonder if there's a reason why they ask us to use 2 to 6 instead. I don't see one. I don't see one, so I'm going to be changing that. B is at 5, -4. Not changing it, but reducing it. Okay. Excuse me. Here's our segment. The ratio is 2 to 6. The 2 to 6 also means 1 to 3, right? It's a fraction. 2 6 is a ratio is a fraction, right? So I divide those by 2. Now, 1 on one side and 3 on the other side. 1 plus 3 is 4, or 2 plus 6 is 8. We're going to go 1/4, 1/4 of the way to B from A. So let's fall and run a certain amount down 1, 2, 3, 4, 5, 6, and over 1, 2, 3, 4, 5, 6, 7, 8. At least that's going to be a clean number. 1/4 of 8 is 2. So we'll go 2 over. And 1/4 of -6 is -1.5. So we'll go 1.5 down. So for P, starting at A's values at -3, -3, comma, 2. Let's take the -3 and add 2 to the right. And let's take the 2 and go 1.5 down from there. And that'll be -1, comma, 0.5. So -1, comma, 0.5. Here's P. That is 1/4 of the way over in a 1 to 3 ratio, or 2 to 6. It's 2/8 of the way in a ratio where this is 2 and that's 6. All right, those are those 4 problems, and it looks like we might have to do something similar to it on this set here. In 21 and 22, draw a segment with the given length. Construct the point that divides the segment to the given ratio. Maybe I should have looked closer at what they said in the lecture thing, because I didn't notice that they mentioned a length before. Let me pause. I'm going to pause this and see where they mentioned length on their own compass construction. Give me 1 second. Okay, I just checked the thing quickly. It doesn't show anything about lengths, but what you'll do means you need a ruler for the part. So I'll use the ruler thing. Obviously, my ruler is a different, like, size than yours for whatever, but I'll show you the idea of what you would do given the ruler. So I'm going to make a 3-inch line and then go off of that. So draw a segment with the given length, construct the point that divides the segment in the given ratio. Okay, so what you first do is take a ruler and draw a 3-inch length. After that, you're set. You don't need the ruler anymore. Well, you need a straight edge still, but you make your 3-inch line, and so that works for me. So there's my 3-inch line. Let me get rid of the ruler. Actually, let me cut the ruler so I can paste it in case I have to use it for the next problem, which I do. Okay, so here's what we're going to do. We have, I'll call this segment length AB, which is 3 inches long. And we're going to separate this in what is it? Construct the point that divides the segment in the given ratio 1:4. I think that means that if this length was 1, then this length is 4 like this. I think it's the same thing that we were looking at before. I apologize if it's... I think that's it. Okay, anyway. So 1:4 ratio like that. So we're going to do kind of similar things that we did before. So in a 1:4 ratio, we need to know that 1 plus 4 is 5, which means we're going to divide this into 5 congruent parts. So this is the part that the lecture brought this up as well. What you do is you draw a line on here that's off, from A or whatever, that's off of that axis, and we construct congruent arc marks on here. Okay, I'll show you what I mean. We draw compass. We construct congruent arc marks on here of equal width, whatever you want them to be. I guess the farther the better, as long as they can all fit on there. But I need 5 of them. So this ain't going to be best here, but I'll try. So like 1, and then from here 2, and from here, we'll see if this will actually reach. It doesn't quite hit right on the thing. Good enough. 3, 4, and okay, doesn't quite hit. Let me extend this. 5. Okay, fine. Okay, so those 5 widths, right? I don't know how long they were. I just set some size and did that. But here's what I'm going to now do. Shoot. I actually don't remember what I want to do from here. I have to copy angles. Oh, this is going to be a lot. So I have to draw lines now to segment AB in such a way, so like this, I'm going to draw this one to here, in such a way that all the other ones would basically need to be parallel. So I need to make one that's parallel to this one here and parallel to this one here and all that, so they stay in proportion, so these can all be equal widths. But to make them parallel, we have to copy this angle that is now made up here from black and green. The black and green together make an angle, and we need all these to be the exact same angle. So in order to make angles, let's flip this thing over. This is going to take a little bit of time. In order to make angles here that are congruent, we have to do a little arc thingy. So arc here and an arc here. I guess I'm just going to do a bunch of ring arcs. So arc. Oh, well, at least that's good news. You can do them all at the same time. So arc and arc and arc. We've done angle, we've copied angles before, so this isn't anything new unless it's your first time looking at it, in which case, I don't know. Your teacher should have taught you compass construction this way. And by the way, I apologize if I'm not looking at my screen thing when I'm looking at my picture, so I apologize if I ever do something like this and you can't see what's at the bottom. I have to look at my compass more so and make these things happen. Now we got to find out the width from this arc to the line, like that. That's about as close as I can make it. The width from the arc to the line right there. And all these need to copy and do that same thing. I need to go the other way though. So let's go this way and do the same thing because we're on this line. So let's find out what that width is like that. That's not that close. That's also not that close. I don't know how to change. I can't snap it anywhere between this. See where it says 34 and 38? There's no in between for this thing. It's just terrible. So I'll just pretend like I'm doing the best that I can with this. So like this looks like, oh yeah, that's so close. but it's not really. So maybe if I just go off the side a little bit, find out where that intersects there. And again, if these aren't perfectly parallel, that's the problem with this thing going from 34 to 38. You saw it for yourself. You see that I can't do it perfectly, but I'll just try and do the best I can here. Maybe next time I'll make the compass thing a little bit bigger. I don't know how much bigger I can make it, though, and still fit it on this page. So quite a bit happening there. And it looks like that's going to intersect at the bottom. Now I draw lines from the blue arc. I'm going to do those green lines again. It's kind of a lot of things to do. When you're like, why can't you just take 3 and divide it by 5? I know, right? You probably could. All right, so I need to draw it from this line, from this arc, through this arc right through that line right there. And remember, it was farther out, so I'm going to kind of estimate what looks right to me. But it looks like it should kind of strike through these things here. And what we're doing is we're creating equal lengths on AB divided into fifths. Divided into fifths because we need to construct a 1:4 ratio from wherever this point P basically will be. So kind of like that. So all that stuff led to this thing right here. In the 1:4 ratio, we now found this point as that length that would make this 1:4 ratio, such as that. And if you know 3 inches divided by 5 is 0.6 inches, that means that this is 0.6 inches, and this is 2.4 inches, like that. But that's the 1:4 ratio. 2.4 is 4 times the amount of 0.6, like that. But it's this guy right there. Construct the point that divides the segment. It's this one here. I could call it P for now, I guess. And that's the answer. All right, there's number 21. Let's do the same thing for number 22. Now, 22, we do 2 inches. Oh, let's do this. Let's look at how close I was. How many inches were we talking about? 0.6? Oh, I can't tell. I can't use this ruler stuff for it. All right, so, that's why I can't make this much bigger, because 2 inches is just 2 inches no matter how you make it. I could make the ruler bigger, but I don't think that's going to be the point of this. You have small space to work with as well. All right, so here's my 2-inch segment this time. Right there. We're going to do the same-esque thing. Very similar in that we have this... I'm going to make this bigger, if that might help. I don't know. But we're going to do a 2:3. Oh, let me move this thing over. We're going to do a 2:3 ratio. Now, 2:3 ratio means... wait, hold on. 2 plus 3 is 5. So we're going to divide this into 5 parts, just like we did before, only I made this part bigger, and I'm going to shoot it down to here. Voom, 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 voom. Like that. And... 1, 2, 3, 4, 5. And what we're going to do here is 2 to 3 is 5. 2/5. 2/5 of 2 inches is 0.8 inches, basically, and that's how far off we're going to go from this thing here. So from our A to B, this is 2 inches here. Let's do this compass thing again. Let's create arcs of certain widths. Not so far out that it doesn't work. I want to try and thin these out just a little bit, though. Let's make them a little less apparent. So like that. 1, that's significantly less apparent. Hopefully you can see that on the screen. 2, 3, probably still going to be too far and overshoot. Yep, looks like it. 4, and 5, just barely overshoots. So let's go ahead and extend that out. You know what the other problem is? I don't know if I'm on that same line anymore. Okay, cool. So the first one, I'll make it a little more visible. This green one I'm going to do here. We're going to basically copy that angle over and over to these other guys here, the black and the green. Let's copy that angle by drawing ourselves some arcs. Fascinating. Okay, so, and again, this is going to be one of those things where you can't see the bottom. Sorry about that. We're now focused just on the angle copying right here. Let's do... I'll do this a little bit darker here. So copy this arc here over and over. Oop. Over and over. Oop. Over and over. Come on. you can see it. Oop. Oop. Once I let go, it snaps out. It snaps off the thing. It doesn't look like I can get right on it, so I'll do. Whoa. So I'll go this way, not that way. Okay. So now let's find that width of all these arcs that we have. Not that width. Flip it over. Let's find this width right here. Too far. Is this going to be right, or is this going to snap? Oh, darn it. Well, the snap won't be perfect here, as was before. So I have to do the best I can and just say whatever this was, just go a little bit lower than each little arc, okay? So lower than each little arc, and let's see how it goes. It's a little bit lower. Yeah, I don't know how much I missed the compass stuff. Okay, especially when these widths just snap into place. And hopefully you're just understanding what listen, if you know how to copy angles, then you know exactly what I'm doing here. If you don't know how to copy angles, then maybe you don't. But this is basically a practice that teachers should teach to begin with, and I'm just doing the problem at this stage. Too big and too thick. So from here through that line, all the way down to the bottom. Looks pretty parallel to me. I'll take it. And then from this line here, down to the bottom. This might be a little bit lighter than the other things, though. Maybe not as parallel, but that's okay. Here down to the bottom. Like that. And here down to the bottom. Like that. Ooh, interesting snap. Okay, so we divided these into fifths. We got to go 2/5 of the way from here. So 1, 2. There's 2/5 of the way. Here's that P. Boom, like so. It's a small little P. Boom. Okay. Okay. Great. I don't know how perfect it was, but great. Love it. Okay. Let's go. Now, oh, by the way, I probably spent more time doing this than I needed to, as far as once I got these arcs here, I probably didn't need to do this 5 times. I just needed this one. You know what I mean? So I probably overdid these problems. Apologies. Like basically once I did all those, this is the only angle I needed to copy there. Spent more time on that than need be. Maybe we should look at it like that. Maybe that's part of the point of this, is they're like, hey, only do this amount there. And for this one, only do. So, okay, maybe that's why the problem took a little bit longer, because I probably didn't have to copy these this many times. But they're just showing how you can break it up into that and only do that many like that. So that one and this one here. And that would be 2/5. Okay, let's move forward. Error analysis. Describe and correct the error in solving for x. I'm just going to guess they built an incorrect proportion. Let's see, number 23. They have AB... They have AB over BC, nothing wrong so far, equals, CD over AD, something wrong with that. Notice they went from left triangle to right triangle start, that's fine, and then they did right triangle to left triangle. So the parts don't correspond. That's the main issue. That's as best as I can say it. You know, the parts don't correspond in the proportion. Directing from the left triangle, or directing from the triangles left to right on the left side of the equation, and then right to left on the right side of the equation. Sorry, there are left and right triangles and left and right sides of equations. So that's what we have there. Okay, so instead of doing AB over BC is CD over AD, we should be doing AB over BC. You can still do that. BC equals, but now AD over CD. AD over CD. Like so. So 10 over 16 equals not 14 over x, but x over 14. All right, 10 over 16 is 5/8. And 14 times 5 is 70. Divide by 8x is 8.75, I believe that would be. All right, there's number 23. Number 24, error analysis. Describe and correct the error in the student's reasoning. 24. Okay, because BD over CD equals AB over AC, so far so good. As far as proportionality, that's something you can do. It might work. And BD equals CD, it follows that AB equals AC. No. The problem... I know what the answer is. I'm trying to think of how to say it. They have the right thing that would stand to reason in a case. The problem is we don't know that AD so far is only representing a median. We don't know that AD is the bisector of angle BAC. This thing applies for angle bisectors, not for medians. If it was an angle bisector and a median, then that thing would be true. You'd have basically an isosceles triangle with a thing. There's a lot of things that would be involved. The inherent issue is that we do not know AD is a bisector of angle ABC, BAC. This theorem, and I forget the theorem's name, unfortunately. This theorem holds for angle bisectors only. So when it says correct it, I can't necessarily really correct what it is that we're talking about in this case because we don't have an angle bisector. AB is not equal to BC, or at least not necessarily true. Not necessarily true. So I guess it was incorrect for me to even state that BD over CD equals AB over AC. So actually, let me say that. BD, so I said that was correct. What I meant was that that aligns with the proportionality that we would go by. The problem is we don't have an angle bisector. We have a median. So angle bisectors only, not medians. Hello? Once we probably look at the proof, we'll know what to do with that. Okay, number 25 and 26. Find the value of x for which PQ is parallel to RS. So basically, we'll need the proportionality that would hold true within this. So I can set something up here. I can say something like 2x plus 4 over 5. Right? The top parts of the triangle, boom, the split parts, equals 3x plus 5 over 7. Let's solve for the x's and see what happens here. Nothing to reduce, cross multiply. 7 times 2x plus 4 equals 5 times the quantity 3x plus 5. Let's do distribution. 14x plus 28 equals 15x plus 25. Subtract 14x over, you get x. Subtract 25 over, you get 3. So this should be the x that holds up. Let's double check and see that it works. Let's try PS as 2 times 3 plus 4, which is 10. And let's check out QR, which is 3 times 3 plus 5, which is 14. Does 10 over 5, which is 2, equal 14 over 7, which is 2? Yes, it does. So that all checks out. 10 over 5 equals 14 over 7. Bing! Seems to work. Okay. Number 26. Number 26. Let's work this out. Let's do 12 over 2x minus 2 equals 21 over 3x minus 1. Now this could reduce. You could divide everything by 2. Let's save it. 12 times 3x minus 1 cross multiply equals 21 times 2x minus 2. Distribute. 36x minus 12 equals 42x minus 42. Wowzers. Subtract 36, add 42, divide by 6, you get x equals 5. Let's double check that and see what that one looks like. The length of segment RT is 2 times 5 minus 2, which is 8. And the length of segment ST is 3 times 2 minus 1, which is 5. Let's check and see if 12 over 8, 3 halves, is the same as 20. Oh, 5, not 2. 5, which is 14. Hello. See, it's bad when the double check is wrong. 12 over 8, which is 3 halves, equals 21 over 14, which is 3 halves. That one also checks out. See, I was double checking. I was like, uh-oh, 21 over 5. That's not the same thing as 12 over 8. Where did I go wrong? Wasn't quite sure there for a moment. Okay, we fixed it. Here we go. Number 27 and 28 are proofs. This is proving the triangle proportionality theorem and the converse of the triangle proportionality theorem. Now, I'll say this. I've done this proof so many times in my life with students and such that the difference is I do it in a more conventional way. I don't do as much in the 2-column proof format. I'll do it more like this, drawing the 2 triangles, they're parallel, all that. And I'll just call this A, B, and C, D. And then I'll do math to show the things work. I almost want to do this first with you guys so that the proof that I do makes sense, because I might mess up writing things on the proof, because now we got to do steps and justify it using like the division property of equality, stuff like that. So if y'all don't mind, I'm going to begin with something like this and see if it works out for you guys to make sense of. So given that you have parallel lines here, then we know that these 2 triangles are similar. We can do like an angle-angle thing, right? Corresponding angles congruent, reflexive property there. And so we'd have this triangle similar to this triangle, which means then, you know, we have 2 separate triangles that look like these guys here, AC, and then this is A plus B and C plus D, like that. So we could then say a ratio A over A plus B equals C over C plus D. If you cross multiply these, you get A times C plus D equals C times A plus B. If you distribute AC plus AD, and let's keep this alphabetical. This is AC plus BC plus BC. Let's rewrite these instead, though, so that now we have like C's on one side of the equation and D's on one side of the equation. You know, something. Wait, hold on a second. Did I write something wrong? AC plus AD, AC plus BC. No, I did not. I want to rewrite things so that... Why do I have so many C's on here? Something seems wrong. Hold on. No, I have 3 A's and 3 C's. Okay, that's fine. Let's rewrite this so that... Now I haven't done this proof in a while. Oh, AC's cancel. I totally didn't see that. Let's subtract the AC's. Okay, so now we have AD equals BC. And if I divide both sides by D and divide both sides by C, you get A over C equals B over D. That's one version that you could write. A over C equals B over D. If I do it in the side splitter theorem way, I can divide both sides by B and divide both sides by D. I get A over B equals C over D, you know, like that. So A over B equals C over D. So you can see where there are instances where those things show up and you get those answers, and that's what we're looking for. This is what our proof is going to do, but we're going to be using these letters, RT and TQ and things like that. So we're going to have to keep the things in mind that we had. We're going to have to call things distributive property and stuff like that. But first, we prove the triangles are similar. So we got to prove that QT over TR equals SU over UR. So the way that they would have done this one is they would have divided both sides, I guess, by A and by C, and they'd have D over C equals B over A, which is, of course, another version of it. Okay, so let's go ahead and do the proof. And by the way, the other one is similar-esque when it comes to proof. You're given that and prove that they're parallel. I mean, from there, you have to... Well, I guess I don't know. You're going to have to prove triangles are similar by side angle side or something like that. Proportionality. So there's that. We'll come up with it when we're ready. All right, statements and reasons. Number 27. I was wondering, I'm like, why do I have so many C's and so many A's? I didn't even see the letters for what they were. We definitely had AC's there. All right, so let's start with the givens. We are given that, or the given, that segment QS is parallel to segment TU. All right, let's go ahead and prove these two triangles are similar to begin with. Because those are parallel, we can do something like, hey, this angle is congruent to this angle by corresponding angles theorem. So let's call that angle Q congruent to angle UTR. That's corresponding angles theorem. Now let's go to, you could do another corresponding angles theorem. I'm just going to say reflexive property. I want to be diverse. Angle R congruent to itself by the reflexive property of congruence. Reflexive property. So by angle, I can say that these two triangles are similar. That's triangle, the small guy is RTU. And the big guy, actually, let's do the big one first because I said angle Q on the left side. I'm pretty particular about that. If I say Q here, I mean the big triangle. So RQS is similar to triangle RTU. That's by angle similarity theorem. Okay, with the angle similarity theorem, we can use the triangle proportionality that we've done in the past here. Not yet the side splitter, excuse me, not triangle proportionality theorem, but the proportionality of the sides of these two triangles. So I could say something like RQ, and I am using RQ first, RQ over RT, big over small, of corresponding parts, RQ over RT equals RS over RU. Equals RS over RU. This is corresponding sides of similar triangles are proportional. I think I've written that before. I wrote the abbreviation and then I spelled out what it was, but I'm telling you out loud what that is. Corresponding sides of similar triangles are proportional. Let's go with it. Now, here's the thing, right? We want to eventually have something that says QT. In fact, I'm probably going to reorder the letters on these. I'm calling them RQ and RT. I probably want to say Q, QR, and TR and stuff like that. It seems like they're going the other way. So let's do that. Let's say QR over TR equals SR over UR. Seems like they're saving R for last. But see, eventually I want to use QT, and eventually I want to use SU, and eventually I want to not make this so ugly looking. So let's talk about the fact that QT is, and I want to do this in one step, and I hope it's okay, that QT's length is from taking QR minus, am I allowed to do this? QR minus TR. This is a form of the segment addition postulate. You know, one way is to say QT plus TR equals QR, but I'm subtracting. Am I allowed to do that just in one step like that, or do I have to show both of those steps? I don't really know, so I'm kind of asking you guys. I feel like you have to kind of, well, you know what? I don't need to get QT by itself, right? The goal is to substitute. So let's actually do it this way. Let's actually say QR is QT plus TR. QR is QT plus TR, because I got to think of it like my proof, right? I have A plus B here, and that's what I want to build. I actually want the A plus B as a part of it. So QR is QT plus TR, and then, wait, hold on, I just lost my other one. What was my other one? SR equals SU plus UR. So here's my segment addition postulate. And then let's substitute for QR and for SR to have QT plus TR, I'd substituted for QR, over TR equals, and for SR I have SU plus UR over UR. So that's substitution, property of equality. I'll just write substitution. Okay, now what did I do from here? I think I multiplied both sides by essentially the TR. I cross-multiplied. Cross-multiplication is not a reason that you can call something anything, but let's essentially do cross-multiplication. UR times QT plus TR. This is going to look very weird when I do the distribution after, because these aren't variables. They're like full-bore letters. So I don't know if this is going to look very good. Equals TR times SU plus UR. That is the multiplication. It's cross multiplication, but the multiplication property of equality. All right, now a distribution, and then we'll do the subtraction property of equality and all that jazz. So let's do, I'll put UR times QT plus UR times TR equals TR times SU plus, and this is also UR times TR. See, these are the ones that are going to cancel. Hold on, distributive. UR times TR. This is the distributive property. Not of equality, it's just the distributive property. Distributive property, and notice how both these have a UR plus TR, or UR times TR that are added, and I'm going to subtract them both out. They're both going to be gone. So I'll be left with UR times QT equals TR times SU. That was the subtraction property of equality that got rid of these two right there. So subtraction property of equality. And then last is just division property of equality. I want to make it look like QT over TR equals SU over UR. So I want to divide both sides by UR, basically. Divide both sides here by UR and divide both sides by TR, like that. So now it's going to look like QT over divide both sides by UR, so I need to divide them both, and divide both sides by TR. Boom. So the URs are going to go, TRs are going to go. So QT over TR equals SU over UR, division property of equality. Boom, like that. And that'll be it. So I know I wrote some of the work in those ones beforehand, but I did them in different colors to kind of establish that that wasn't part of the actual problem that I was doing there. But I got to the proof, and that's it. So it's the same thing as what I wrote above, just with like, I just used single variables, and I didn't state reasons why, but I did them mathematically. So, and it's things that students understand, right? If I do that with my students, they can follow along if I ask them. The thing they always get caught up with actually in a statement like this is, and let's rewrite these in order. C times A is AC. They go, what? Or saying what I divide both sides by at the end. Everything else they understand, the similar triangles and all that. All right, we got to do another proof, but that one kind of hurt my hand a lot. So let's jump into number 28. Let's do the converse of the triangle proportionality theorem. Let me take a drink here before I get started. I'm actually pretty low on water now. Definitely hit a crawl though as well, total slowdown. So the converse, I think, will probably get us in the. This one might be faster. This one might be faster. I feel like what I can do. Oh no, it's the split part. Ooh, I don't know. Oh, let me think about that. I wonder if I'm allowed to introduce a I wonder if I'm allowed to force in new addition, because think about where these ones came to be. I'm going to go back to the other page in a moment. Think about how we did the previous one. At some point, and I didn't cross them out, but at some point, oh yes I did. At some point, two items canceled out there, right? I subtracted them out. So if we're going to go kind of backwards, and that's what I feel like we're going to do. It's almost a backwards thing to get to this part here. In order to go kind of backwards, I feel like you have to introduce two things to add out of thin air. Call it the addition property of equality, if you will, because that's what's going to happen. But I feel like you need to introduce something out of thin air to make that happen. And I don't really know, because I haven't done it in this direction, right? So let's try that and see if that works. Basically, adding something that wasn't there to begin with. If subtraction property of equality goes on this problem, then addition property of equality probably goes on, or of the previous problem, then addition property of equality probably goes on this problem here. So let's go ahead and try this one out. We're going to start with the given, and we have zy over yw equals zx over xv. We got to prove that yx is parallel to wv. Okay, so the thing is, yw is the split part, and Vx is the split part. So those are the ones on the bottom. If I want it to ring similarly to what I did before, well, it doesn't matter. It's okay if it's the... Oh, it's the split part. Hold on. But I want to add something to them. Okay, if I want to add something to them, I feel like I need them on top so that I can add something to them. So I'm going to do a rewrite of this thing. I'm going to raise everything to the negative first power. I don't know if you call that the exponential property of equality. I'm just going to say it's a rewrite. If I do a rewrite of the proportion right here, yw over zy equals z xv, xv over zx, xv over zx. Actually, let's do this. Let's do, instead of this, let's do a cross multiplication, because, right? Let me think backwards. This comes from a division, right? So let's multiply both sides. Let's do zy times xv. It'll look a little confusing, but we just saw that last time. Equals zx times yw. So that's the multiplication property of equality. Yeah, so I think I will just go kind of backwards here. But I need to see what I need to add in that I can then factor out. So last time I distributed, right? This time I'm going to do a factorization of something. So let's add the same thing to both sides. Now, what did I have to take out from both sides to make this work? I have to think in terms of these letters they have here. UR and TR. Wait, where's the diagram? UR and TR were the parts that... Do they multiply together? UR times TR? So they multiply together. So basically I need to do some sort of YZ times XZ thing that goes into both, or ZY. ZY times ZX. I need this on both sides, and I think you'll see why in a moment. ZY times ZX equals, and then here I still have ZX plus, I just don't have much room, ZX times YW plus the same ZY times ZX. So I just inserted these ones into there. It seems random, but that's what I was saying. I need some sort of creation of this thing here. So this is the addition property of equality. And it's for a very specific reason, though. This will allow me to seek a common factor that exists in both sets of these things here. In this set exists a common factor of zy. Let's factor it out. And in here you have xv plus zx. And on this side, you can factor a zx out. And here you'll have yw plus zy. So factorization, factoring, I guess property. If there's a distributive property, then I guess there's a factoring property. I guess, Mr. Wayne. So there's that. Now from here, didn't this come from a cross multiplication? Oh, xv plus zx, where is that? Xv plus zx is this entire thing right here. So let's do a substitution. VZ, which way do they go? They go from Z to whatever. So I'll say ZV. ZV is XV. I'll just write XV plus ZX. It's those things. Plus ZX. And then ZW is YW plus ZY. That is the segment addition postulate. And we're going to substitute in those things. Segment addition postulate. So let's put ZV in place of that there. So ZY times ZV. ZY times ZV equals ZX times, and then ZW is taking place of YW plus that. So ZW, that's substitution. Oops, that should be a 6. So substitution property of equality. So stick for place. Now let's divide to write a proportion. I don't know what the best version is. Let's do the zy and zx on top, just like it shows on the given. Let's do zy and let's have zx on top. We're going to divide both sides by zw and divide both sides by zv. So if I divide both sides by ZW, it goes over here. If I divide both sides by ZV, it goes over here. This is the division property of equality. Now, what we just created here was a proportion of, check this out, let me show you. I'm going to mark it here. This is ZY over ZW equals ZX over ZV, something that's required in similar triangles. Now we have the whole of the small and the whole of the big over the whole of the small and the whole of the big. So this is part of our set for doing a side angle side similarity. I'm not going to be able to do side, side, side. I know nothing about YX and WV, but what I do know is that angle Z is congruent to itself. Angle Z is congruent to itself by the reflexive property of equality. Reflexive property. Now I have triangle similarity by side, angle, side. These two are in proportion with each other side lengthwise. These two are in proportional, etc. So now I can say these two triangles are similar. Triangle ZYX, the smaller triangle, is similar to triangle ZWV by side, angle, side similarity theorem. That was from section 8.5. And corresponding angles of similar triangles are congruent. So now that I know the triangles are similar, now we know that corresponding angles will be congruent. For example, this angle is congruent to this angle right here because the triangles are similar. So I can call that angle ZYX and angle W, for example, because corresponding angles of similar triangles are congruent. And corresponding parts of congruent triangles are congruent, but these are similar. So the last thing, y is YX parallel. How do we know that YX is parallel to WV? Why are these two parallel here? Because the converse of the corresponding angles theorem. Those two angles are congruent, so YX is parallel to WY because the converse of the corresponding angles theorem. That was 11 steps. How long was the other one? Let's see which one was longer. Well, they're both 11 steps, so there you go. All right, both 11 steps there. So this one there. Fun, right? Love it, love it, love it. All right, let's keep moving forward. Let's hope no more proofs or constructions and stuff. All right, number 29. Modeling with mathematics. The real estate term lake frontage refers to the distance along the edge of a piece of property that touches a lake. Oh, lake frontage. I was saying like lake frontage. Lake frontage. So this is lake frontage. Find the lake frontage to the nearest tenth of each lot shown. So the whole thing's 174 yards. And it's split up into components. And this probably works more along the lines of, no pun intended, along the lines of what we did with the graphs in a way, because you want to figure out how far along 48 is in this set. Like, here's what I'm thinking. Here's what I'm thinking. 48. Here, I'm going to copy this over. There's a proportionality involved, right? There's a proportionality involved because of the parallel lines. We might understand that much, hopefully. Now, if you add up 48, 55, and 61, you get this entire thing here. And I don't know what that is. 103 and 164, I believe. Let me do that twice. The other way. 116 and... yeah, 164. Okay, 164 yards. This amount should be 48. And I don't know if this is how we're supposed to do the problem. Suddenly I'm not thinking maybe clearly about how to do it. But because the whole thing's 174, I want to find the thing to the nearest tenth for these. we can do 48 over 164 times 174 here. We can do 55 over 164 times 174 here. This is the only way I'm really thinking about how to do the problem right. And 61 over 164 times 174 here. Those amounts will get us what those things are. Let me use my calculator for that. I'm never not going to use that. 48 over 164 times 174. 50.9 yards. This is rounded to the nearest tenth. And then let's do 55 over 164 times 174. That's 58.4 yards. Let me first make sure 48 plus 55. I triple checked, but I want to, whoopsie. Calculator 48 plus, hold on. 48 plus, okay, 164. Okay. And then the last one is 61 over 164 times 174. And I get 64.7 yards. So 64.7 yards. So these belong to kind of part A. So part A is there. Okay, part B. In general, the more lake frontage a lot has, the higher its selling price. Which lots should be listed for the highest price? Well, lot C should be listed for the highest price because it has the most lake frontage. So, yeah, lot C. Okay, anyway. Lot, I mean, I don't really know if I'm messing something up there. It just seems like an obvious answer. Okay, so there's part B. And then part C, suppose that lot prices are in the same ratio as lake frontages. What? If the least expensive, the proportion, okay. If the least expensive lot is $250,000, what are the prices of the other lots? Explain your reasoning. So if the least expensive A, 50.9 yards, and listen, you generally don't want to use rounded numbers for things, but I'm not keeping the other number. It doesn't seem like they want us to keep the old number there. I'll leave it unless I use the 48. I should be allowed to use the 48 because it keeps this proportion in mind. So I don't see there's a reason why I don't need to. So I'm going to use the 48 instead. I'm going to use the 48, the 55, and the 61 for these because they should go in proportion, right? 48 over 50.9 should be the same as 55 over 58.4 and 61 over 64.7. They should be in proportion. Okay, so let's just keep the 48 here. If the least expensive lot is $250,000, that's lot A. So $250,000 over 48 yards, and it doesn't matter, I can either use the 48 or 50.9, but 48 is exact. What are the prices of the other lots? Explain your reasoning. So lot B price, I'll write lot B later, over 55 yards is what we can come up with here. And then I'll do the same thing for lot C. So I'll do 250,000 over, now my explanation is in my math, just so you know, it's proportionality, over 48 is lot C over 61 yards. That should be fine. So I'll do some cross multiplication and solving stuff here. Give me a moment. 48 times B is 250,000 times 55, and I'm sure you could reduce the 250,000 thing. I'm good. 13750,000, and B, not an exact answer, but $286,458.33 approximately. I don't know if you should just round to the nearest dollar or what. So for this other one, 48C equals 61 times 250,000, and that's 1525000 divided by 48. And I'm getting 317,708.33. Always keep a quarter, a nickel, and 3 pennies at hand. They seem to come quite in handy for all the problems that we have here. So, there it is. All right, so let's go ahead and take a look at what's next here. Number 30. Okay. Number 30, modeling with mathematics. Your school lies directly between your house and the movie theater. Oh no, to get to the movie theater, I have to first go to school. The distance from your house to the school is 1/4 of the distance from the school to the movie theater. What point on the graph represents your school? 1/4 of the distance. Okay, from the school. Okay, so let's copy paste this guy so we don't have to plot new points again. We are sticking to that same principle as before. It's not saying that your school is 1/4 of the way to the movie theater. It says from house to school is 1/4 the distance away. So you do have that 1-to-4 ratio that we're still playing with in one of these cases here. 1 plus 4 is 5. So basically, distance from your house to school is 1/4 the distance to school to the movie theater. So basically, school could be about like right here. If this is x and this is 4 times farther away. So this is x and that's 4 times farther away like that. So we'll have to figure those things out. Let's figure out this rise and run from house to movie theater like that. My movie theaters are a lot closer than the school I teach. 1, 2, 3, 4. Up 4 over 1, 2, 3, 4, 5, 6, 7, 8, 9. But it's also not quite on a line either to go to a movie theater and to my school. They're just different places. Okay, so let's find out. So 5. Let's figure out 1/5 of 4 and 1/5 of 9. Let's do the 1/5 of 9 first. That's the x. That's 9/5 or 1.8. And 1/5 of 4 is 0.8. So we're going to be adding, I'll put P for the school's point. I'm going to be adding, so -4 plus and -2 plus, these are the locations of home, -4 plus 1.8 and -2 plus 0.8. And we'll get school's location at -2.2, comma -1.2 like this. So -2.2 comma -1.2 is going to kind of look like that right there. That's point P, and that is where your school is located on that point. All right, 10 more questions. Hopefully, I look at number 32 and it looks scary, and I can't even see it in full. So, number 31. In the construction on page 503, explain why you can apply the triangle proportionality theorem in step 3. Okay, let's find this page 503 thing that they're talking about. I don't know if I have all the page numbers saved on here, so let's see if we can find it. Okay, page 503 is this guy. So they're saying step 3, explain why you can use the proportionality theorem over here. Well, now the lines are parallel. Is that what they mean? Explain why you can use the theorem now, because you have now constructed parallel lines. Yeah. I don't know what else that they want, that they're asking of me in that situation, but that is the thing, and the triangle proportionality theorem says when you have that, then you have thing and yes. So, in the construction page 503, explain why you can apply the triangle proportionality theorem in step 3. So, the best way I can say it is, in step 3, you construct parallel lines in a triangular, in a triangle, where one line can represent the third side, and another line can be a segment inside that is parallel. This is the concept, is the frontage. This is the catalyst. I guess catalyst is the word behind the triangle proportionality theorem. You first need this to be true before you do anything else. Basically, you can now divide this part, divide by this part, is this part, you know, things like that within there. All right, number 32 looks freaky, so I don't know what we're going to do here. Use the diagram with the auxiliary line drawn to write a paragraph proof of the three parallel lines theorem. I like to call it this whole thing the side splitter theorem. Guys, look up side splitter theorem and see what I'm talking about with this. All right, given the parallel lines there, prove CB over BA equals DE over EF. Okay, I am looking at the auxiliary line as a way to look at these this as a triangle similarity thing here to drew proportionality of this over this is this over that. And then in the same way, we can do it with a triangle here to say this over this is this over that. And then we do a substitution with the division that we had to make that work. I feel like that's what they want us to go for. So let's kind of play with that and see if that's enough. So, and sorry if that's not the way. That's my plan that I'm saying given the auxiliary line we have. Okay, so statements. The only problem is it's going to take long. Reasons. You can tell I value my time. All right, given. Whoops. Given K1 is parallel to K sub 2 is parallel to K sub 3. So parallel lines allow us to use, basically at this stage, we can almost go straight into the triangle proportionality theorem thing. Because K1 is parallel to K2. Okay, you know what? I don't think this proof can take too long. I don't think we have to prove triangle similarity anymore. We can use the triangle proportionality theorem, I think, straight up right here. And I think it's basically a substitution. So it actually isn't that bad. Because K1 is parallel to K2, and you have a triangle setting in there using the triangle proportionality theorem, I think we can go straight into saying things like AB, wait, they want to say CB. Okay, let's go in the way they have it. CB over, I think this is going to be fast actually. CB over BA equals, this might be really fast. Am I doing this too fast? DE over EF, excuse me, DE, wait, where's E? Oh, E is not that point. Oh, we don't have a point determined on the line. Am I not allowed to just say that there's a point that's right here on the line? Can I call this a point P? Ooh, I was thinking that was E before. I don't know if I'm allowed to. Let me just call that point P. So then I have to put something in between that says something like that, right? Let's do something like, let P be intersection of, I feel like I should use G, A, B, C, D, E, F, G. Intersection of auxiliary line and K2. Auxiliary line and K2. I'll call that construction. By permission. Let me do it, please. All right, step 3, CB over BA equals DP over PA. That's how I want to put this. DP over PA. That's the triangle proportionality theorem. Now, that's not the only time I'm going to use that. Triangle proportionality theorem. Step 4, let's now look at this kind of triangle. I know there's still a P there. So let's kind of now look at this triangle here and do the same thing, but keep in the order that the proof is going to want. DE and EF and DP and PA and stuff like that. So now we can say DP, because it's still parallel lines. Now we're looking at parallel lines K2 and K3. DP over PA equals DE over EF. So that is Also triangle proportionality theorem. And I think it's just step 5 now. Step 5, I won't call it a substitution. I'll call it transitive property. Two things equal to the same thing are equal to each other. So these guys are going to be equal to each other, and that's the proof statement. CB, okay, this looked scary, and I think this is good. CB over BA equals DE over EF, transitive property of equality. I think once I kind of defined that point, and I think I'm allowed to do that. I think once I defined that point, then we were good. I just wish that they did that for me so I'd feel more comfortable in doing that. Looks good to me. Okay, that's it. Number 33, critical thinking. In triangle LMN, the angle bisector of angle M also bisects LN. I'm going to get water here soon too because I'm dry after this problem. Classify triangle LMN as specifically as possible. Justify your answer. Okay. Let's draw something random to see what they're talking about. So here's triangle LMN. And they said the angle bisector of angle M bisector, also bisects, oh, I mentioned this before, also bisects LN. Boom. Justify your answer of the blah, 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 blah. So, okay, this is an isosceles triangle. I can't say how I know. I want to use a triangle congruence thing for this, but this is an isosceles triangle. For this to both be a bisector, well, here, let's kind of do what that one proof was trying to do that one time. I want to justify it using where we're at in this stage right here. Oh, here's how I can do it. Check this out. It is kind of what they were saying before. So because of the angle bisector, let's call this point P. Because it's an angle bisector, I can say something like LP over NP equals LM over ML over MN. But because LP equals NP, then this is 1. You know, LP over NP equals 1 because they're the same. So ML over MN, and multiply both sides by MN, you get MN equals ML. If MN equals ML, then MN as a segment is congruent to ML, which is also what isosceles triangles do. So that's my justification right there, using the proportionality of that. And that really was kind of the catalyst that one other problem had. It was the error analysis one that made the assumption that a median would be enough to kind of call these things congruent. No, because they made the false assumption that, you know, you didn't need an angle bisector, and you did. The angle bisector was required, and this one has it. So cool. This makes sure that you have an isosceles triangle as a result of what's there. All right, let me refill my drink. Give me 1 second. Okay, I'm back. All right. Okay, number 34. During a football game, the quarterback throws the ball to the receiver. Okay, interesting diagram. The receiver is between two defensive players as shown. If player 1 is closer to the quarterback, wait, hold on. Quarterback, the receiver is between two defensive players. Receivers here. Player 1 is closer to the quarterback when the ball is thrown. Both defensive players move at the same speed. Which player will reach the receiver first? Explain your reasoning. Player 1. Player 1 will reach the receiver first because of the proportionality. I don't know what it's called. Oh, it's down on number 35. Because of the triangle angle bisector theorem. Triangle angle bisector theorem providing a proportionality that shows if he is, I'm assuming it's a he, closer to the quarterback, then he'll also be proportionally closer. I'm over explaining it. Proportionally closer to the receiver. Yeah. Hopefully that makes sense. Basically, it's working the theorem in play here. If this is like 2 to 1 and this is like 3 to or 6 to 3, something like that. It's that kind of idea that's in play. Okay. I really noticed the how do you see it questions are often really, not to say easy, but really fast. Maybe really easy. They're just like, here it is with a real life scenario, but it's just one of your basic questions. And then you have something like proving a theorem on number 35 with another auxiliary line, although the last one wasn't bad. Use the diagram with the auxiliary lines drawn, lines, the blue ones, to write a paragraph proof of the triangle angle bisector theorem. All right, given the angle bisector, prove that thing here. So in order to do that proof, you want to do, I guess you just want triangle similarity. Is this, am I to see this as one line right here, there, a straight line, I suppose? So which two triangles do you think that we want to find similar in this case here, if any, right? Well, these are parallel. So, if these are parallel, then we could just build a boom over boom equals boom over boom. And these are the same. Are these the same? Is there a way to say that these are the same? Hold on. I want to build this in a way that makes sense to me. Does AX equal XZ in some sort of way? That's what I want to figure out. What's the way that... right here, alternate interior angles. Okay, so here's going to be my proof, my idea. We don't need triangle similarity necessarily. We can just use our triangle proportionality theorem. We have parallel lines. See, the problem is you see the different colors. It looks to me like this thing kind of bends out, but it doesn't. By the triangle proportionality theorem, we can say that this over this is this over that. Right? Agreed? Agreed. Okay. This over this equals this over that. But now we got to do this over this equals this over that. Something along those lines. And then we can rewrite it as we need to. Or we can start with that. YW over WZ. Perfect. We just got to show that this is the same length as that. And we can by saying alternate interior angles here. And then this one's congruent with that. Therefore, they have... This is an isosceles triangle. Those are going to be the same. So, and we can substitute. Okay. I have my plan. So let's do a statements reasons. And let's see what we got. I'm just glad I don't have to redraw it. I'm sorry if you do. Statements reasons. Let's go with number 1, the given. YXW is congruent to angle WXZ. Okay. Paragraph proof. Oh boy. I didn't even see that. I'm sorry. Did I have to do paragraph? Uh-oh. Let me go back. Oh. Did I have to do paragraph proofs for... No. Guys, will you forgive me for not doing a paragraph proof of this one? Is that okay? I'm catching myself with this one. I'll do a paragraph proof for this. Apologize I didn't do a paragraph proof for the other. The only problem with paragraph proofs is doing the symbols and writing some things above them and stuff. Okay. So XW is an angle bisector because angle YXW, see, this is where things are weird, because angle YXW is congruent to angle WXZ. And now my formatting is going to be just terrible. So XW is an angle bisector. Oh, I don't think we need to know it's a bisector. I mean, that's the given that leads to this, but I don't think I need to know I don't think I need to use the phrase bisector for this to work on the way that it does. So let's do that again. We are given, I'll say we're given. We are given that angle YXW is congruent to angle WXZ. Okay. Now, drawing auxiliary lines, this doesn't work with the things here. Drawing auxiliary lines AX and AZ so that AZ is parallel to XW, we can use the triangle proportionality theorem to state that, and I'm going to write this one out, YW over WZ equals YX over XA. Our basic thing from here on out is to show that XA is the same thing as XZ, okay? So that's my next bout here. Okay, so angle A is congruent. So angle A is congruent to angle WXZ, and angle, like, because that's like a given, and angle, well, sort of, it's marked as such. They're parallel lines, so that works. And angle WXZ is congruent to angle XZA because they are alternate interior angles, or because the alternate interior angle theorem, lines are parallel, alternate interior angles are congruent. Therefore, angle A is congruent to angle XZA by the transitive property of equality. So now I just found out that these two, boom, boom, are congruent to each other. And it's the thing for isosceles triangles, right? Therefore, let's see. This means that XA, we used XA earlier, right? Yep, XA is equal to XZ by the base angles theorem of isosceles triangles, basically. So by substitution, then, and then the final concluding statement. So I'm going to substitute XA. I'll keep that as an equals. YW over WZ equals YX over, instead of XA, I can write XZ, and that's the one that we wanted to prove there. So all the congruent things I need congruent there. I need segments here, Those are lengths, congruent there, and congruent there. And then I leave these ones are lengths right there just to make a substitution straight up. All right, that's number 35. Number 36, thought-provoking. Write the converse of the triangle angle bisector theorem. Is the converse true? Justify your answer. The original says if you have an angle bisector, boom, boom, then these are proportional. The latter says if they're proportional, then you basically have an angle bisector. Do I write it using a paragraph proof? Let's go for it. Given that... given that, I guess we have the same auxiliary line thing, right? So given that, boom, I don't really want the circled thing. So given that these are in proportion to each other, is that kind of what I want to say? Do I want to start? Is that what we're saying? Given the proportionality? So given the proportionality, I mean, we're literally going to have to go back to all the other things about like the isosceles triangle bits or whatever. I'm questioning my life choices right now. Oh, they just said write the converse. They didn't say write a proof. Okay. What are they asking us to do then? Okay, write the converse. Okay, so now we're saying if a ray passes through, here, and those things are in proportion, then the ray is bisecting the angle. So the way I'd say this is if a ray that passes through the vertex of a triangle, divides the opposite side into segments, and those lengths are proportional, whose lengths are proportional, To the sides of the triangle? To the other two sides? To the other two sides of the triangle? Then the ray bisects the angle through which it passes. The angle bisects the angle through which it passes. Is it true? I believe it would be true because it's dividing it into proportional parts, right? That's the point of what that ray is doing. The ray is basically creating similar triangles. So, yes, this is true because the ray is dividing the triangle into proportional parts. And those proportional parts mean that you're going to have corresponding parts that are congruent. So, so the angles must be congruent. Right? That's how that triangle similarity goes. Corresponding angles to similar triangles are congruent, and that's how that works. I thought we were supposed to write a proof. Okay, anyway. I'm really having trouble reading my own problems, just like I didn't write a paragraph proof for the one, and I feel so bad. You guys were like, no, but teacher, I wanted a paragraph proof. Sorry. Reasoning. How is the triangle mid-segment theorem related to the triangle proportionality theorem? Explain your reasoning. Well, I brought this up really quickly before. The triangle mid-segment theorem is the triangle proportionality theorem, but for midpoints. If you don't recall the triangle mid-segment theorem, it's if you have a triangle, let me kind of like make one up. If you have a triangle, then its midpoints, boom, are in such a way that this is not only parallel, which is some way that it relates, but this is also, this is half of whatever this is. Right? So there's a proportionality within that. And then there's more. I guess they're saying what are the things you can say. This is also a 1-to-2 ratio relationship right here. Y to 2, Y, and, Y to Y. This is Y to Y here and Z to Z. I mean, that makes sense because proportionality, right? Midpoints. So, I don't know what to say for it specifically. How's it related? I mean, it's all the rage, man. It's everything about it. It's everything that you can see about it that still holds true, the side splitter stuff. So how's the triangle mid-segment theorem related? The mid-segment theorem, let me do it a little bigger. The triangle mid-segment theorem has parallel lines, features parallel lines much like the condition for the triangle proportionality theorem. And you really don't need to know the x over 2x part. That's not really a key to this. For the triangle proportionality theorem, and shows that a midpoint dividing a segment into two congruent parts. Let's see what I want to say about this. Basically, it makes sense that this is a y and z, not just for the midpoint action, but the way that this thing gets doubled into 2x. I don't know how I want to say that best, though. How does it relate? I think it's just saying that it's a very special case of one. I don't think I have to do all these other parts right here. So, demonstrating a special case of that theorem where the segment passes through the midpoints of those sides. It's just a specific version of it, and it seems to work itself out the way that it does. I don't know. Sometimes it's hard for me to answer questions in the way that I don't know. It's like, I do the same thing sometimes too. Like, I create a question for my students, and when I know the answer to it, it's easy. You know? It's not as easy when you're hearing it for the first time and you're not really sure what to do. All right, 3 more questions. Oh, I see construction and a proof. But first, making an argument. 2 people leave points A and B at the same time. They intend to meet at point C at the same time. The person who leaves point A walks at a speed of 3 miles per hour. You and a friend are trying to determine how fast the person who leaves point B must walk. Your friend claims you need to know the length of segment AC. Is your friend correct? Explain your reasoning. No, your friend's not correct. They don't need to know that. So if you're traveling 3 miles per hour and you got to go 0.6 miles, then you can figure out how long it's going to take, right? It's just let me just bring some science, some math up to you guys for this. Work this out. Distance equals rate times time. We have the distance and we have the rate. We don't know the time in hours. If we divide both sides by 3, we'll figure out the time. 0.6 over 3, which is 0.2 hours. Person B, so this is all for person A, right? Time for person A, distance for person A, all that kind of stuff. Person B, Person B, sorry, I keep saying that over and over. Person B now has a distance overall that needs to be traveled with this. Wait, I'm sorry. 0.9. Ooh. Wait, 0.6 is not the whole way. Wait a minute. 0.6 is not the whole way. That's just 0.2 hours to get to that part. Let me think about that. You don't need to know the length of AC. Okay, I got it. I'm overthinking what I need to do. I thought 0.6 miles was the whole distance from A to C, but now that totally doesn't make sense because the question's within there. So let's ignore the distance equals rate times time. What you need to know is how fast. Oh, duh, it says that. You're trying to determine how fast the person must walk. All you need to know is the rate from AD to BE. So no, you just need the AD to BE rate. However, 0.6 miles to 0.9 miles will give you, that's 2/3 of whatever. So person B or person A needs to walk 2/3 the speed of person B to cover that, right? Person A needs to walk. I misrepresented the problem. I apologize. To walk 0.6 over 0.9 equals 2/3 the speed of person B. Basically, person B needs to walk, and they're not asking us to do all this, but I am going to do it. So 2 to 3 equals 3 miles per hour to X miles per hour, right? It's going to be 4.5, I believe. 2x is 9, so x is 4.5 miles per hour, person B. So person B needs to, walk 50% faster than person A to kind of compensate for that. I wasn't hearing what the question was asking before. I thought they were saying to get the distance from here, do you need the full distance AC or could you use other measures? I'm like, well, no, I don't know. All right, number 39, 2 more questions. Construction. Whoa. Hold on. Go back up. Final boss battle later. Given segments with lengths R, S, and T, construct a segment of length X such that R over S equals T over X. Let's copy and paste those and see what the heck I want to do with those. I'm going to make these lengths in a way. I'm going to give myself my own versions of them. So this will be my R. Oops, I didn't get 2 endpoints. I can still do that. So this will be my R. This will be my S. I mean, this won't all be perfect, but you're going to do the same thing I do if you're looking at these problems. I just need to put them out. And this will be my T. This way I can mold these to my liking here. This will be my T. And I know they want to use the compass to copy them down. I might do that eventually. Let me show you how you would use the compass to copy them down. I just need to go a fast track way. So here you would just create this width, go like, okay, here's that width here. So this needs to be, the same width like that. So basically 3 of those, right? Okay, so you got that much. Cool, cool, cool. Okay, so here's R, S, and T. R, S, and T. Now what do they want? Construct a segment of length x such that R over S equals T over x. So if you want R over S to equal T over X, I can think of either something in terms of side splitter theorem. I can think of something in terms of that triangle angle bisector one. We've done angle bisectors. Although I wonder if... I guess that'll be fine. Wait, hold on. I'm trying to think if I can do the angle bisector one, and that if I need to make an angle bisector first, because I don't know how long these would need to be for it to actually fit in that way. I'm trying to see if that's possible. If not, I'm going to do the triangle proportionality theorem one. But R over S equals T over X. Okay, let's do the triangle proportionality one. I think it'll make more sense for me. So, okay, I probably didn't need to copy these over. So let's just do this. Let's find this length, boom, like that. I'm going to create, well, you know what? I can do this, right? So I want you guys to do this. Create segments R and S and put them with each other like this. Boom and boom. You can put them flat if you like. That's totally okay. We're going to be making T bend at an angle a little bit. I don't know why I can't line this up perfectly. That's okay. We'll just leave it like that. So here's R and here's S. You're basically going to find this length for R. Boom, draw that, take the width for S, and then draw another thing that's collinear, like that. You can draw the segment first and go after it. You can see why I'm going to have problems with it. That's why I'm not doing it. So, like that. Okay, so we made R and S. Now, what you want to do here equals T over X. You'll make T, so I'll kind of simulate it this time. You stretch out and find out T's length here. Okay, kind of like that. Boom, boom. And especially since I'm going to bend T, I'm going to actually do this time. So I'll draw T along here. Like that. So this can be my T, right? Because that can be that length. So that's still T's length. Now X will go along this line, right? And I'll make sure to extend that actually even for itself for X later. But here's what I need to do. I need to make parallel lines here, and I need to copy this same line and put it over here. And wherever this parallel line intersects with this line will be X's length. I was wondering if I could do it with the angle bisector one. I still don't know, but I can at least do it with this one as a for sure. And that's what I'll do. So I need to copy this angle by doing stuff. I can do that width there and repeat that right here. And then I need to find that width between those two parts of the arc where they intersect. So I can do that and, whoops, I gotta flip it though. So 72 with the 72. So 72 on this side like that. That's fine. It'll still copy the angle. Okay, and then I just draw a line. So I'm going to draw a line through here, boom, like this. And then I need to keep extending this line outward. Oh, hold on. Let's extend this one outward more. I need to, and that should have been parallel. It doesn't even look close to parallel because I can't copy angles right. Let's pretend like that was close. Okay, that looks better, right? And then this copies over here. You have to recall, guys, that this compass construction thing doesn't work well on my software. So I copy that over like that. And then that's where those two things intersect. So if this is T, this is going to be X. See, this follows the triangle proportionality theorem that these are parallel lines, right? That was the point of copying the angle. Copying the angle gives me congruent corresponding angles. Congruent corresponding angles gives me parallel lines. Parallel lines allows me to set up the triangle proportionality theorem that R over S equals T over X. And this would be X's length of that if these two lines are indeed parallel. If I copied congruent angles by kind of forcing that in. Okay, that is number 39. I got one more, number 40, and I shudder in fear over what this one is. I've never heard of Seva's theorem. I think he's made up. Number 40. Excuse me. Proving Seve's theorem. If P is any point inside triangle ABC, then AY over YC times CX over XB times BZ over ZA equals 1. Hint, draw segments parallel. I have to draw more? Oh, they just say have these drawn. Draw segments parallel to BY through A and C as shown. Okay. Apply the triangle proportionality theorem to triangle ACM. Okay. Where's, oh, because this part that's parallel. So they're looking at that. Apply the theorem to ACM. Now, I'm unlikely to do a, like, 2-column proof or even paragraph proof. I might just do more math and say them out loud if that's okay. Show that triangle APN, where's N, is similar to triangle MPC, CXM, where's X? Oh, geez. CXM is similar to BXP. Okay, well, we'll do this in time. And BZP is similar to AZN. Okay, so that's a lot. So let's work off that drawing and see what we can do. Some of it scares me, but I think we can work it out. Okay, so I'm unlikely, like I said, to do like a paragraph proof, 2-column proof, things like that. I just want to work out some of the math and go off that, because otherwise it'll be just a long thing here. So let's look at this triangle. Let's use the triangle proportionality theorem off of that. And with it, I can say something like AY, let's write this in green, AY over YC equals, I mean, they give me good hints. AY over YC equals AP over PM. Now, it's likely we're going to do substitution within here or something to make that work. You can even see that AY over YC is a part of what we're going to do. But somewhere AP over PM is going to change. We're going to have other things that can work with that. Actually, I can now see why we want to do something like that. So now that we got that one set up, now take a look once again at this AP over PM. Let's use a different color now. They said now take a look and prove that those two bigger triangles are similar, which I think they're talking about these two right here. They said prove that these two triangles are similar. That'll be pretty easy to do. So listen, these two triangles are similar because why? Because vertical angles show that these two are congruent, and alternate interior angles, remember these lines are parallel, alternate interior angles show that these lines are congruent. By angle, these two triangles would be similar. So triangle, let's see, which ones do they call them? I lost my page suddenly. Hold on. Triangle APN. I mean, I can write it however I want. I just wanted to use the same thing they have. Triangle APN is similar to triangle MPC by angle. Therefore, and here's the thing, this has AP and PM on it. AP over PM equals are we using CP? What do they have? They have CX and XB. Do they have MC? No. Let's do, what are the other ones they want to show that are similar after that? CXM. Where's CXM? So I'm going to use CM and AN because we got to use those later. I'll say MC. MC over AN. So now by, not substitution, but transitive property of equality with these two together, we now have a statement that can say AY over YC equals MC over AN. Not that we're done with that stuff yet, but now both of these will separately do their own little triangles within. Now we're going to look at, let's kind of, Invisalign those things a little bit, make them a little less. And now we're going to show that these two triangles are similar here. Wait. Let's thicken that a little bit. I want to show that these two triangles are similar here. Where, listen, it's the same stuff, the angle stuff. We can go and say that these are vertical angles here, and you have alternate interior angles here. well, I can still use 2, huh? Alternate interior angles here. And then we can do the same thing on the other side. It's all angle, guys. This is why, like I said, if I did this whole thing in paragraph proof thing, we'd be here all night. So these two are similar as well for the same kinds of sets that we have. Where to use green? This kind of ran out of colors I want to use. How about just black? So here we have, again, vertical, and you don't have to use vertical angles. You can use the alternate interior stuff for both these. That's still fine. So here I can say triangle, how do they call it? CXM. CXM is similar to triangle BXP. Also by angle. Again, vertical angles and alternate interior and stuff. I'm not writing all that out. But there's that one. And let's use the MC portion of it. MC is to PB. MC is to PB as... Which letters do they use? CX and XB. CX is to XB. CX is to XB. But PB is not a part of the other... Oh, but PB is going to be shared on both of these. Okay. So let me figure out how that's going to look when all's said and done there. Because I don't actually know. And because this other set here, we can say that this triangle BZP is similar to triangle AZN, also with angle. And now we're going to use this AN somehow. So AN over... Well, PB or BP? I'm going to put BP because this thing uses... I guess I can use that. AN over BP. BP is PB. Equals... I guess I'll write it as PB, even though we don't write it the same way. AN over PB equals, and then what do we need? BZ over ZA. Ooh, then I need PB on top here. PB over AN, it's hard enough without having to write the proof stuff, equals BZ over ZA. Okay, in what world can I now use this MC over AN stuff right here? If I multiply these together, if that makes sense, these equal each other in such a way that if I, look, if I marry these two, if I multiply both sides by this here and this here into that, so multiply and multiply, what I get, fortunately for myself, is I'll have PB over AN times MC over PB. This is where these cancel out. These are gone. Equals BZ over ZA times CX over XB. Now, this is a lot of what you see on these ones right here. That is all a part of that. This is written the other way. That's okay. We can get there. And MC over AN is over here, all right? AY over YC equals MC over AN. So AY, so this is a substitution, right? You can now take this and substitute into here. So AY over YC equals let me write it the other way. YC, not YZ, over YC equals CX over XB times BZ over ZA. The problem is, it looks like I have something reversed. MC over AN, if they equal each other, then dividing by this would give you 1, not multiplying by it. So what did I do incorrectly there? AY AY over YC equals... Oh, hold on. Where did this come from? Sorry, I'm going to go back to here. Let me... I'm not going to pause, but AY over YC is AP over PM. Boom. Now, AP over PM... Oh, I have this backwards. Okay, so let me do this. AP over PM is not MC over CM. So let's change this. Wait, will that change a lot? Where did I put AP over PM? AP over PM is the same as AP over PM. Where did this go? Where did I use this again? Did I use this again? Where did I use this? Oh, AY. Okay, so let's do this. Let's change this. Not AP over PM, but... Because where's MC? MC is the big triangle. AN is... Okay, MC is this triangle. AN is this triangle. But I was first doing this... What was it? AP and PM. AP over PM. Oh, we were talking about these triangles here. So this triangle and this triangle. So AP over PM, it's AP over MP equals MC. Okay, so we got to do this. We got to put PM on top. We got to put PM on top. AP on bottom. Now, AP over PM is AY over YC. We got to now swap AY over YC down here. This is YC over AY. This is YC over AY. YC over AY. So now this substitutes here, and this is YC over AY. Okay. YC over AY. Okay, perfect. Okay, now if I multiply both sides by AY over YC, basically dividing both sides by YC over AY, if I multiply both sides by AY over YC like this, then on this side, all this cancels out, or becomes 1, rather, and I can write it exactly how they have it. AY over YC times CX over XB times BZ over ZA equals 1. Okay, so I misrepresented one of the proportionalities early on by the way that I wrote it, but it looks like I remedied that just by flipping this over. So hopefully you recognize what I did here. When I have PM over AP, or hopefully you know why I did this straight up, but when I substituted here, AY over YC is AP over PM. If I flip-flop that, that's YC over AY equals PM over AP. And this is PM over AP, so YC over AY just took its place down there. And that's what we have that there. All right, so that's the last one. It was, that was an ordeal for sure. And guys, that ought to do it for this one. This is Mr. Robinson. I want to thank you so much for watching. And that is the end of the chapter when it comes to the new stuff of section-based things. After this is just review things. I'll be doing an actual chapter review. I'll do the chapter test and cumulative assessment. And I'm going to do one of those little are you ready things as well. I think that that's going to fare well for what we do. Take care, guys. Thank you. I will see you in the next one.